Hello students. In this video, we will talk about another important AC bridge which is commonly known as sharing bridge. This sharing bridge is used to find capacitance of a unknown capacitor. Okay. So just like the previous lecture, we have studied already that how a Maxwell bridge can be used to find out unknown inductance. Similarly, here also we will try to find out the unknown capacitance value. Okay. So without further ado, let me share my screen and explain how it works actually. Okay. Okay, hope my screen is visible to all of you now. So see, this is the circuit diagram of a sharing bridge. As you can see, since this is an AC bridge, some resistances and capacitances are involved in this circuit along with a alternating voltage source. Let's say it is E, okay, having the magnitude capital E with a frequency, angular frequency, let's say omega. Okay. So now uh, you can see there are four arms in this bridge. In the first arm, one capacitance and one resistance is involved, denoted by C1 and R1 respectively. Actually, this is marked in red. Why? Because this is unknown capacitance. Okay. So C1 is the capacitance value and R1 is the internal resistance of that capacitor. Okay. So both are unknown. Similarly, in second arm, we have attached a capacitor called C2. In third arm, only one resistance is involved, that is R3. And in the fourth arm, the C4 is connected in parallel to resistance R4. Okay. So now our objective is to find out these two quantities C1 and R1 in terms of either C4, C2 or any combinations of all these things. Okay. So before going to start our experiment, let me explain how to calculate this bridge balance equation. Okay, how to form this bridge balance equation, which helps you to understand why what is going on inside this bridge. Okay, so first of all, if you consider the first arm of this bridge, here the impedance, that means that impedance can be calculated as R1 plus j omega C1. Why? Because due to this small resistance R1, this is your directly impedance of due to this resistance is, as you know, that is only R1, but impedance due to this capacitance, it will be 1 by j omega C1, correct? And since they are connected in series, so we can use R1 plus 1 by j omega C1. Okay, fine. Similarly, in case of, if you see the fourth arm, if you see the fourth arm here, C4 is connected in parallel with R4. So that means what is the impedance? I mean, due to R4, it is only R4, simply R4. Okay. And what is the impedance due to C4? It will be 1 by j omega C4. And since they are connected in parallel, so we can use this symbol R4 parallel to 1 by j omega C4. So as you know, that the formula, like, it will be R4 into 1 by j omega C4 divided by R4 plus 1 by j omega C4. Okay. So I am not simplifying it. Actually, I will show you how to derive this equation later on. Okay. But as of now, you just understand, since there are two components R4 and C4 and they are connected in parallel, so we are applying a formula which is like R4 parallel to 1 by j omega C4. Now, consider these two, another, that means second arm of this bridge, it is only containing one capacitance, so it will be straightforward 1 by j omega C2. And the for the third arm, the impedance will be very simple, it will be only R3. Okay. So now, at the null condition, okay, so this is called the bridge balanced equation. At the null condition, this criteria should be satisfied. That means Z1 Z4 is equal to Z2 Z3. Now you all of you now have what is the value of Z1 Z2 Z3 and Z4. If I put all those values in this equation, then we will get an equation like this one. See, this is the circuit diagram, okay? And if I place all this value like here R3 into 1 by j omega C2, so this is here R3 into j omega C2. So this is the R2 R3 side, and in your right left hand side of this equation, the parallel formula will work like this one is the parallel formula, and this is the series formula R1 plus j omega C1. So now you can see here we can also write it like minus j R3 omega by C2, correct? So there is no real part, only imaginary term is there. In this right hand side of this expression, it can be written as minus j R3 by omega C2, and which is the imaginary part, right? Similarly, after multiplying these two, we can of course get a plus jb kind of form, and from there, if you compare these two equation, you will get that R1, and after comparing, you can reduce this formula. R1 is equal to R3 C4 by C2, and C1 is equal to R4 C2 by C3. So from this equation number 3 and 4, it is very clear that to find out the capacitance value C1, you need to know only R4, C2, and R3. So varying these three parameters C2, R3, and R4, we can calculate C1 easily. Similarly, in case of R1 also, by varying C2, C4, and R3, we can get the value of R1. Okay. So this is the working principle of this bridge. This is how, since R3, R4, C2 all are known to you, then you can easily measure the C1, correct? By varying the C2. Let's say your R3 and R4 is fixed, then also by varying C2, you can calculate the value of C1. Okay. So now go to the simulator tab. Your job is to perform this experiment in this VLabs platform. The link will be given in the description of this video. Okay. So now follow these procedures usually. Okay. For example, apply supply voltage 3 volt. From here, you can reduce it to 3 volt. You can set 3 volt of any arbitrary frequency. So keep it 500 hertz, no problem. Okay. Then next job is to set unknown capacitance from the set capacitor value. So here is your set capacitor value. So I can make it like you can set any value. Okay. In between this UF means U stands for actually microfarad. Okay. U means micro. Okay. So 100 microfarad, and this is 0.0001 microfarad. So you can set any value in between this range, okay, from 0.000 microfarad to 100 microfarad. Okay, so let me set it for 1 farad or 1 microfarad. So if you set it for 1 microfarad, then and to set this 1 microfarad, you have to click on the set button. Okay, and after that, you switch on the kit. Okay, so if you switch on the kit, then see you can see a sharp deflection in this dial. Okay, now your job is very simple. By varying this R3, R4, C2, C4, by using this sliding switch, you have to get the null position, okay, or null condition you have to achieve. After achieving null condition, you go to the measure capacitor value. Okay, you have to go to measure capacitor value and then click on simulate, and after clicking on simulate, you will get the capacitor value here. Okay, however, here it is not in null position, so it is giving an erroneous value. So I can show you a correct value after trial, okay, as an instance. So for example, this one I have already studied or performed this experiment earlier, and this is the result. Okay, so where I get this for 1 um, uh, microfarad, I got the null position. Okay, here, and this is the calculated value of the capacitance. It is showing that 1 microfarad. Okay, it's almost correct. Okay, almost correct. The error is 0.02. If it is 0.00, then you will get more accurate value. Okay, but As of now, that 0.02 or 0.03 is also permissible, provided that the main error should be less than 15%, as you all know. Okay, so this is the value, one, yes, I mean typical set of values here. Okay, so in this way you have to perform the experiment. In your lab report, you have to only mention what is your input voltage, what is your frequency, okay, and what is the set capacitor value, that means what is your unknown true value of your unknown capacitor, and then what is the calculated value of the capacitance, and then please mention R3, R4, C2, C4 with their proper units, and then make a table and submit in your lab records. Okay, so thank you, that's all for today.